students, good evening to all of you, and today my name is Sumit. I'm a BTech graduate from IIT Bombay and a master teacher at Vedantu. Alright, so today we are starting a mini series on thermodynamics, that is for physics, because we have thermodynamics for chemistry as well, my dear students. Alright, now the first session that we are going to look at basically is going to be on your first law of thermodynamics. Now, before we go ahead and study about your first law of thermodynamics, let us go and understand what is a thermodynamic system. Alright students, you might have done that while you were doing Newton's law. Like anything that you are basically observing, my dear students, that is the system. Alright, and anything which is outside the system, it is called as my surrounding. So, to get started with, first we will look at what is a thermodynamic system. Alright students, now to begin with, a thermodynamic system, if you can say, is basically something which is under study or which you're trying to look at and observe. Alright, now this thermodynamic system, if we can actually look at, it is divided into three segments, my dear students. Now what are the three segments we are talking about here? Firstly, we have got an open system. Next, in the line, we have got a closed system. And finally, we have got something called as an isolated system, my dear students. Okay. Now, what is an open system? See, it's very simple. Anything that is a system, I mean, probably I'm saying it as a system, might be looking at very complicated. See, students, the ultimate thing is even your body as such is a system. We eat food. That is like, we put matter into us, alright, and then we can also look at the entire thing that we are exchanging energy between us and our surrounding in some form or the other. I mean, because we might be climbing up a hill and spending energy on that particular thing. So, in a way, there is exchange of matter and energy between us and the surrounding, right? In the same way, any form of a thermodynamic system, based on whether it's open, whether it's closed, or whether it's isolated, they exchange matter and energy between the system and the surrounding. Alright students, now let us understand, okay, what is an open system. Now open system is something which would actually exchange mass as well as energy, alright, between the system and the surrounding. A closed system is going to exchange energy but not mass. And if I have an isolated system, it is not going to exchange either energy or mass. Now, students, let us do something. Let us take an example of each type of system and let us look at into that. Fine. So, what do we have first? We have got an open system, isn't it, students? Now, for an open system, let's say we take a vessel and we start boiling water. Alright. So, in order to do that, let's put some fire and we definitely see the temperature of this particular thing is going to go up. Alright. Now, you see all these molecules of water which are present out here. Alright. When you start heating them, what happens? Definitely, you will feel the surface out here is hot, so it's kind of exchanging energy. Energy is going from this heated up part to the surroundings out here. Alright. Now, besides that, you will see this molecules will get converted into vapor. The water molecules will get converted into vapor and go out into the surrounding. So this particular system, I mean, the vessel, the molecules, and the fire out here, okay, now this is doing what? Okay, it is exchanging mass and energy with the surrounding. That means it is an open system, my dear students. Okay, now next let us look at what is a closed system. Clear? So a closed system, let us try and understand that. It exchanges energy but not mass. Isn't it? We had talked about it. So, let us take a beaker, put some water, a hot water into it. Now, at this particular state, my dear students, it's actually an open system, right? Probably it's this water molecules kind of going up, I mean, it's losing heat, alright. But, in case I put a lid on top of it, all right, and do not allow these vapor, the water molecules, like to escape out of this particular system, then my dear students, in this particular format, the energy will be actually moving out, right? This system is going to exchange energy with the surrounding, but the water molecules are going to be tapped inside the system. So it will be exchanging energy but not mass. Is this clear? Chalo, let us look at next at what is our isolated system. I think this isolated system is kind of present in everyone's house, okay? When we have a thermos flask, okay, which we generally use to keep your hot water, like warm in the winter days, all right, students, this is exactly that. This is your isolated system. It is neither going to exchange energy, all right, or mass with the surrounding, all right, students. Fine. Now let us try and understand, after we have got to know what are the different kinds of system, because this is exactly what is going to be a study of in the entire of thermodynamics. Like what is the kind of a system that we are trying to observe here and performing our experiments with. Clear? Now we will try to look at what is our first law of thermodynamics, right? This is exactly our today's topic. First law of thermodynamics. Now in my first law of thermodynamics, before we can kind of go ahead, let us understand the principle on which the first law of thermodynamics actually works. It is based on the conservation of energy. Now very simple idea. You've got a building, and on top of the building I kind of put a ball out here, okay? Now students, what does this ball have out here? Potential. It kind of falls down. So we see that as it falls down by a height h, the above part, it had only potential energy, which was equals to your mgh, isn't it? Now as it kind of fell down, all its potential energy got converted, isn't it? And it got converted into what? Your kinetic energy. So whatever you had as your potential energy out here, that is your mgh, has got converted into half mv square. So as per the principle of conservation of energy, my dear students, we can definitely put it here that my mgh is equal to half mv square. Now this kind of a principle is applicable at so many different places in our lives. Don't you see that? I mean, if you look at this particular room, all the electrical energy which is surrounding me has got converted into light energy, and it's providing so much light in this particular room. Or as a matter of fact, your ACs, geysers, everything, there's exchange of energy, right? But energy can neither be created nor it can be destroyed. It can only be transferred from one format to the other format, students. Clear? Now my first law of thermodynamics is basically based on this principle out here. Alright, let us look at this conservation of energy principle in a thermodynamic system. Clear? Now, what do we have here? Our first law of thermodynamics based on the conservation of energy. So whatever is the energy provided, that is the energy before, is equals to the energy after. The things are kind of balanced in this particular situation. All right. Now, let us look at the application of this in a thermodynamic system. So this is my vessel out here, students. If you kind of look at, this is my vessel out here. It's filled up with some gas molecules, right? Now the molecules are kind of moving randomly in this particular situation, and what do? You start heating it. Now as you start heating it, what is going to happen? The molecules are starting to move very, very randomly, and we can also observe the temperature of the gas is also increasing. So there are like two observations that we kind of see here. I mean, if in a vessel you kind of have some gas, all right, and you start heating it, there are two things that is happening here. The temperature is increasing, and associated with the temperature, the internal energy of the gas also increases, my dear students. All right. So whatever was the heat energy that was kind of provided to this, all right, so you provided it some kind of a heat from here. So let me say all these heat can be written as delta Q. All right, students. So this delta Q is being provided to this particular system out here, and because of which the temperature rises, and along with it I can see the internal energy kind of rises. All right, so this change in the internal energy here is directly related to my increase in temperature. Now what else can possibly happen because you provided it heat besides the increase in the internal energy? My dear students, we will see that this piston, okay, as you would observe that when it was initially here at this point, there would be pressure acting out here. So let's say this pressure is like P, okay, and this might have moved ahead by, let's say, delta X. Clear? And we have the area of this particular piston as A. All right, then students, what is the force which is basically acting on this? The force which is acting on the piston can be written as P into A, right? And say this kind of moves up by a distance delta X, then how much is the work done by the pressure? Note that this pressure is kind of constant out here, okay? So the work done, we will be representing it as delta W will be force into the displacement, which can be written as pressure into area into delta X. So dear students, this could be written as P into delta V. That means whatever is the change in the volume that is in this particular section, that is equal to the work done. All right, students. So we can look at this entire thing as, that is, if you provided it heat, what happened? We saw its temperature increases. Along with the temperature, because the temperature has increased, the internal energy has increased. All right, and as the internal energy has increased, we have also seen there has been a change in volume, which kind of told us how much is the work done. All right, now this is exactly, my dear students, the principle of your first law of thermodynamics. That is, you kind of provided delta Q, all right, heat, that is your heat energy got converted into two things. Number one, it increased the internal energy of the gas. Second thing, there was some work done by the gas. Clear? So this delta Q, which was initially provided to the system, it increased its internal energy and it did some work, that is your delta Q is equals to delta U plus delta W, my dear students. Clear? So this is the mathematical way of representing your first law of thermodynamics, and it is based on the conservation of energy. All right. Now, in order to do problems, my dear students, with this particular formula, there is a sign convention that you need to actually remember. Okay, it's a very easy formula, and a lot of questions are based in JEE based and other NEET and competitive examinations on this particular formula here. Okay, so let us look at what is the sign convention that I'm kind of talking about here. Delta Q, if it is supplied to the system, it is considered as positive, and if it is extracted from the system, it is basically your negative, my dear students. Okay, next, delta W, we know if expansion has taken place. If expansion has taken place, then the work is being done by the gas. Now we know if expansion has taken place, delta, what was work done, my dear students? If you observe, the work done, delta W, was equals to P delta V. Now in case your expansion has actually taken place, then delta V will be positive, right? If delta V is positive, then my work done will be positive, that is my expansion has taken place, all right? And in case of your compression, your delta V will be negative, as a result of which the work done will be negative. All right, students, simple explanation. And the third thing that we kind of look at here, that is your internal energy change. Temperature increases, internal energy is positive. Temperature decreases, internal energy is negative. All right. However, in kinetic theory of gases, my dear students, you must have seen a relation between internal energy and change in temperature, which is given as, this is kind of important, that is delta U is equals to NF by 2 R into delta T. Now this part here is kind of constant for a given gas. So in a way, your delta U is directly linked to delta T. Temperature increases, delta T is positive, delta U becomes positive. Temperature decreases, delta T is negative, then delta U automatically becomes negative. Now, my dear students, this is the basic idea of your first law of thermodynamics, and based on this particular principle, let us do a numerical which has appeared in your previous year's JEE examination. Okay? Now, moving ahead, let us just closely look at this particular formula, this particular numerical here. That is, there was this gas which is compressed in this chamber out here. All right. Now, it has been, it was kind of filled in out here, and it got compressed from 2 meter cube to a volume of, so there was this gas of 1 meter cube out here. It kind of got compressed to a volume of 1 meter cube. All right, students. And at a constant pressure of 100 Newton per meter square. And then you supplied some heat at a constant volume, that is of 150 joules of energy. They asked us what is going to be the internal energy change of the gas. Clear? Chalo, let us have a look at this. So, my dear students, we'll take a different color here. Let's take something as black only. Okay. So, we have a gas. So, the gas internally out here, that is your V initial, was 2 meter cube. Right, my dear students? And after that, it got compressed to how much? 1 meter cube. Right, students? Now, based on this, I can find out what is my delta V. Remember, delta is always final minus initial, as a result of which I can write it as final volume minus initial volume. Clear? So what is my final volume? 1 minus 2. So that becomes minus 1 meter cube. Alright, students. Now, what will be the work done? Alright. In this particular case, the work done will be delta W, that is minus P into, we have already taken into consideration. Okay. So delta W will be just P delta V. So pressure, we have seen here, it is at a constant pressure of 100 Newton per meter square. So I'll keep it as 100 and delta V is minus 1. So this will become minus 100 joules. Alright, students. So here we had the calculation of whatever was the work done in the process of compressing 2 meter cube to 1 meter cube at a constant pressure of 100 Newton per meter square. Alright, students. Then, as it kind of got heated, you provided 150 joules of energy. Correct? So, in this case, you provided this heat to the system. So, whether it will be positive or negative, definitely, my dear students, you got it right. It's positive, right? So, delta Q will be positive. That means I can write down my delta Q as equals to plus 150 joules. Alright, 80% of the work is done. Next is what? We need to find out what is the internal energy change. My dear students, this question had actually come for JEE 2014. I mean, like, very simple and based on the fundamentals out here. So we know the standard formula is delta Q is equals to delta U plus delta W, which kind of tells me that my delta Q out here is 150 is equals to delta U. This is what I need to find out. Plus, okay, let me just remove this part. So I know this is like delta U plus delta W. Delta U, I'll keep it as it is. Plus delta W is minus 100. So minus 100. What do I get here? Delta U is equals to plus 250 joules. That means I can clearly observe that my internal energy has increased by 250 joules, my dear students. So option A here is the right answer. Okay, that's it, my dear guys, from this particular session out here. In the next session, we are going to look at your work done calculation through graphical method in any thermodynamic process. Clear? So stay tuned for that. And here in my, so here let me just summarize. Okay, students, in this session here today, we kind of looked at your first law of thermodynamics, which is based on the conservation of energy. That is, your delta Q is equals to delta U plus delta W. All right. So what did we study here? That is, my delta Q is equals to delta U plus delta W. First thing. Second thing, you should know the sign convention for each one of them. This is based on the principle of conservation of energy, simple idea, and that is it that we kind of looked at here. And in the next lecture, what are we going to do? We are going to look at the calculation of work done, all right, through graphical methods. That means I'm going to introduce to you the indicator diagram thing in the next session. Thank you very much, students, and see you very soon. God bless you all.